Okay, in this video I'm going to continue on with my tutorials on thermodynamics and statistical mechanics. This is video number 47 and I'm going to discuss the van der Waals model. This is video number 2 of 3 in this subsection. I'd like to draw your attention to my website universityphysicstutorials.com. So this is video 2 of 3 on the van der Waals model. The previous video to this is number 46, where I derived the functional form of the van der Waals model, and I also listed all the videos which are relevant to this particular subsection. Here what I'm going to do is going to get the Gibbs free energy associated with the van der Waals model. So in the previous video we modified what is in green at the moment is the ideal gas law. We saw that there is a finite molecular volume, so we had to increase the term to V plus NB for a real gas. Also there are attractive molecular forces, so we had to decrease the pressure term with this particular correction value here. We can rearrange for pressure to get the van der Waals pressure as follows. So what we're trying to do is get the Gibbs free energy associated with this particular function. So the thermodynamic identity associated with the Gibbs free energy dG is minus S dt plus V dP plus mu dN. Now if you look at this, if we fix both the temperature and the volume, what we get is that dG dP at temperature, if you fix the temperature, and the number of particles, not the volume, we're going to get V, like that. So that's the relationship between the Gibbs free energy and the pressure. So that's exactly what we're going to do here. We're going to try and get dG dP. Okay, now if you look at this, if we rearrange this as dG is equal to V dP, and do a bit of a sleight of hand, which you will have seen me do in the past, is once again take the partial with respect to volume. And this is the function which we're going to play with in order to get the Gibbs free energy associated with the van der Waals model. So what we need to do now is to get dP dV and associate it with the Gibbs free energy changing with volume. So let's go ahead and do that. So actually, no, I'll leave it there for the moment. We need to get dP dV, or del P del V. So del P del V is just the derivative of this with respect to V. And that's going to be minus nkt over V minus n times B to be squared plus twice a n squared divided by V cubed. Okay, that's just a small bit of differentiation. So I'm going to write that here. So we have del P del V is equal to minus nkt over V minus nB squared plus 2an squared over V cubed. But in order to get the partial with respect to volume for the Gibbs free energy, we need to first multiply by V. So we're going to have V here, and V here. Of course this is going to cancel there. And we also need to move up this del V term up top. So we're going to get the following. Okay, now if we rearrange that, we can write that del G is going to be minus nkt V dV over V minus nB to be squared plus 2a n squared dV over V squared. Next, we know of course that the total Gibbs free energy is simply the integral over simply the integral over its infinitesimal changes. So what we need to do is integrate this function with respect to dG. But of course this is going to be, because we're talking about dG is a function of volume, so we're going to get the integral with respect to volume, of course. Now, to be honest, and this is a question to you the viewer, if you can tell me why I can't do this by integration by parts, I would like to know. But you can't, so you have to do this by substitution. So it's something that personally I'm not clear about. But anyway, I leave that open to you. So let's just rewrite that. We saw that the infinitesimal change in the Gibbs free energy is equal to minus nkt V dV over minus n minus, or V minus NB, excuse me, that's a typo, V minus NB to be squared plus 2an squared dv over v squared. Now the substitution which we have to make, I'm going to call it a, and it has to be v minus nv, or this is the one I'm going to suggest. It doesn't have to be. Of course you can do a number of different substitutions, but this means that dA is equal to dv, and it means that v is equal to a plus nb. Alright, now I'm not going to insult your intelligence. I'm sure you know how to do integration by substitution at this stage. So that means that the total Gibbs free energy is the integral of its infinitesimal changes, and that's going to be equal to minus nkt a plus nb dA over a squared plus 2 small a n squared, the integral of dv over v squared. Alright, or we can rewrite that minus nkt. We have the integral of a over a squared dA. We also have plus the integral of nb over a squared dA, and we can close this off like that, and we also have plus 2an squared, the integral of dv over v squared. So doing the integration, we get minus n times k times t, and we get the natural logarithm of a minus nb over a, like that. We have plus 2 a n squared times minus 1 over v. And putting it all together, we get the Gibbs free energy associated with the van der Waals model as minus nkt, the natural logarithm of v minus nb, minus nb over v minus nb, minus 2an squared over v plus, of course, an integration constant. And that's the Gibbs free energy associated with the van der Waals model. So thanks for watching. Please pass it on to your friends, subscribe to my channel, and you might also visit universityphysicstutorials.com. Thank you.